So just as kind of the last class where we talk about things, just wanted to briefly sort of recap kind of the major frameworks and things that we had discussed. So first is, and this I just made up. This is not Kautz or, anything, too thoughtful, but just as kind of a quick and dirty way to organize some major concepts. So the first thing I thought about was, or you could almost think of this as like, if there was a test in this class, what would we review? There's not, so no one's freaking out. So nervous laughter. The first is, the knowledge, the logic program beforehand. And this seems to be where the bulk of work is. And at NeurIPS this coming year, there's actually a tutorial called Neuro Symbolic Programming. And essentially what they're referring to are paradigms where, as part of what the machine learning person does is they're somehow writing a program that specifies a structure. Yeah.
Just a one-off, a tangent question, but is the tutorial going to be in person or is it virtual?
I don't know. Yeah, I don't know. But there's a better tutorial at AAAI this year. And 23, but it's going to be like this class compressed in like a 2-hour block or something. Yeah. Anyway, enough of that. But I think the idea of thinking of neurosymbolic programming as essentially a way to program structure in a neural network, I think is kind of an interesting idea. I mean, who knows if that'll really catch on or not. I could think more of this as being like a research thing where researchers, who know a lot about logic come up with some kind of canned logical ways to specify structure, and they test it in different things. I would be surprised if we'd ever get to the point where engineers in a company doing machine learning, learn a language and use it to, I don't think it's too far off, but I that seems to me to be a bit more work than kind of like, putting together layers in PyTorch or something. But I mean, kind of interesting to see how these differ from each other, listing them out. You got LNNs where, you parameterize the operators. Well, LTNs parameterizing the symbols themselves. NOR PSL, which I think is, ends up being very different just because of the inference processes based on that optimization problem. You have NOR ASP, where actually they're not really parameterizing anything on the logic side, and they're just relying on the lower neural layers to do all the training. And essentially, it's just a way to push everything through. And then we have ILP methods, and we talked a lot about this. I threw in SatNet. I don't think I'd really call that an ILP method, but it does deal with learning constraints, even though you can't readily get at them right now. I think, what's interesting about ILP is, the whole field of ILP has been generally confined to small problems. I think differentiable ILP, of course, is the same way. They have this combinatorial explosion. I like the direction that those follow-on papers have taken it, and I think there's, probably some legs there. SatNet, I think, is probably because of that symbol grounding paper where they had that overstated result with the Sudoku. SatNet probably doesn't get as much credit as I think it deserves. I think, I think the ability to train a neural net to solve a combinatorial problem, I think a lot of folks don't understand how important that is, and how, a feed-forward network by itself is going to pretty much always fail, big time on those kind of tasks. And I think the idea of learning the combinatorial problem from data, to me, that was, I think, just very appealing. I think there's, if that thing can scale, there's probably a lot of good applications for that in the future. And then we had ontological neural nets, and these things are interesting. They come out of a little bit different community. The semantic web guys like Tom Lukasiewicz and Pascal Hitzler. Here they are this community is traditionally used to a deduction process that is very expensive, like exponential time, because they allow flipping of things between positive and negative and stuff like that. And so traditionally, they've always looked at heuristic approaches that would be sound but incomplete. They look at neural networks as a way to perform that deduction process in a way that approximates deduction. But of course, the downside here is you don't have any explanation as to how it reached that deductive proof. Just gives you a result that they have grounded experimentally. And then the other interesting thing, when I spoke with Hitzler about his work, we got into a little sidebar about inference steps, and he says, yeah, it actually becomes less accurate with the more inference steps that you have, which I thought was also kind of an interesting thing. But again, I don't think this is going to be a universal kind of NSR solution because of the lack of explainability. Then we had, deep symbolic regression and deep symbolic policies. And this is kind of, a little bit broadening of our ideas of what NSR can be. But I mean, honestly, these are symbolic approaches. I think that a lot of the things they've done in there, how they've wedded symbolic regression to reinforcement learning, the ideas of refinement, I think are really important. And I think, if you decide to get into NSR, I think these are some ideas that are worth thinking about. And then finally, we had verification. I don't think I need to say too much about that since that's, we talked about that today. There's an argument against verification being important for NSR, and it goes like this: if your NSR system has a fully symbolic equivalent, what do you need? Verification, you don't really need it anymore. Everything is suddenly trivial. It's just an entailment problem. And that's actually, there's some people that think that way, but I think it's going to take a long time to get NSR to the point where, you have that symbolic representation that maintains all the fidelity of what you learn without any extra magic parameters, and you can check that specification, efficiently. That's going to take a while for that to happen. And so in the meantime, you have stuff like STLnet. And then we also just had some other topics that we talked about. We had that first discussion on optimization. I think that's going to probably be some, really fertile area for NSR because, from what I have seen, other than the guys at IBM, most people aren't looking at the underlying optimization process, and everyone's kind of saying, "Hey, let's just build it on, SGD." There's no rule saying that it has to be that way. I mean, it could still be end to end if you use something else. The clever discussion about data sets, that's probably going to be more important as we go forward in establishing benchmarks for these things. There was like that 20 ILP problem benchmark in the differentiable ILP paper, but those problems are all like, very tiny. And so for anything that's beyond theoretical interest, you're going to need something bigger. So I think we're probably going to see some growth in that. And then symbol grounding / transduction, this whole thing of interfacing between the neural and the symbolic layer. I think there's going to be a lot of challenges there that'll get realized. That Samsung paper I mentioned earlier, was really focused on that with abduction, but even though they achieve some scale over some related approaches like NeurASP, they don't really achieve scale in a real way. I think the whole story of SatNet is a really interesting illustration of how symbol grounding, can go wrong. And, there's a lot of pitfalls there. And that's probably going to, you know, if NSR catches on, this is going to be probably a really hot area of research, I believe. All right, so that's kind of all I have for today. So just open up any other questions or final thoughts as we wrap up the formal part of the course. All right, well, then enjoy the rest of your day. Thanks much.